Last time we learned about constants of proportionality, when the value of a ratio stays the same no matter what. And our first big example was pi, where the circumference of a circle divided by its diameter is always the same, no matter the circle. Another example we looked at was the mass of oxygen in water divided by the mass of hydrogen in water. And no matter how much water you have, and whether the water is ice, or water vapor, or liquid, the ratio is always the same, 8:1. Let's see what other constants of proportionality we can find. For example, are there any constant ratios in the composition of wood? Let's think about what we know about the composition of wood. We know that when wood is heated without oxygen around it, it leaves behind charcoal, creosote, smoke, and water. And we also know that these four things are made of three elements. Charcoal, creosote, and smoke are largely carbon, and water is hydrogen and oxygen. So the question is, do these elements form in wood at certain ratios? Let's see what happens when we measure it out. Here's a piece of wood that we are going to heat in the absence of oxygen. We weigh the original mass, and it's 100 grams. Then we run the experiment and measure the elements that are remaining. Through careful measurement, you would find that the carbon left in the charcoal and the creosote adds up to about 25 grams. And the carbon left in smoke is about 15 grams. So, how much carbon was in the original stick? Well, it's the same that was left at the end, so it's a total of 40 grams. That leaves the other elements, and we know that wood is made up of carbon, hydrogen, and oxygen. And it turns out that the hydrogen and the oxygen pair up in the same ratio as they do in water, or 2:1. So we can ask how much water was in the original stick. Well, if we had 100 grams to begin with, and 40 of it was carbon, that leaves 60 grams of water. Our last question is about our ratio now. What is the ratio of the mass of carbon in the wood to the mass of water in the wood? Well, our carbon was 40 grams, our water was 60 grams, so that gives a ratio of 40:60, or 40/60. For every 40 grams of carbon in this piece of wood, there are 60 grams of water. Let's compare this to another sample of wood. Say we start out with 35 grams. Through careful measurement, you would find that there are approximately 9 grams of carbon left in the charcoal and creosote, 5 grams left in the smoke, giving you a total of 14 grams of carbon in the original stick. So to calculate how much water was in the original stick, we do 35 minus 14 grams of carbon to give us 21 grams of water. Now let's look at this ratio. That's 14 grams of carbon for every 21 grams of water. Before we look at these ratios closely, let's collect one more set of data. Say we start with a 5-gram piece of wood. Well, you would measure that the carbon left over in the charcoal would be approximately 1.5 grams. And you would measure the carbon in the smoke approximately 0.5 grams, giving us a total of 2 grams of carbon in the original stick. Now if we subtract that from the original 5 grams of wood, we would get 3 grams of water that were in the original stick. So now our ratio is 2 grams of carbon to 3 grams of water. Now it's time to look at these ratios. If you look closely, 40:60, 14:21, and 2:3 are all equal. So, the ratio of carbon to water in wood is constant. And we know that the ratio of hydrogen to oxygen in water is fixed. So, in wood, the ratio of carbon to hydrogen to oxygen is always the same. So in answer to our question, are there constant ratios in the composition of wood? Absolutely, because there are patterns in nature, patterns in the way that chemicals combine. Let's look deep inside a piece of wood. These are the atoms that make up a piece of wood, which you learned in Lesson 5 are oxygen, carbon, and hydrogen, and they form in a certain structure or pattern. Let's choose one tiny section of the wood and count the atoms. Inside the circle, you would find 12 oxygens, 12 carbons, and approximately 24 hydrogens. So this gives us one example of how many oxygens and carbons there are compared to how many hydrogens there are. if we take a look at any other section of wood, we should find the exact same pattern, or the exact same ratios. Let's see. Inside this boundary, we count 6 oxygens, 6 carbons, and 12 hydrogens. So if we take a look, the ratio between oxygen, carbon, and hydrogen is the same. There's a factor of 1 between the oxygen and the carbon, and a factor of 2 between those and hydrogen. And so this relationship would hold no matter what piece of wood we look at. And this is the basis for the ratios that early scientists were finding in their measurements. Now let's get back to some things we can actually measure, like chemical reactions. Here's a big hunk of pure carbon. If we were to burn it, it would give off a gas. Now it turns out there's a constant ratio between the mass of carbon burned and the mass of gas released. And that ratio is 3 to 11. So for every 3 grams of carbon you burn, you get 11 grams of gas. So if you start out with 12 grams of carbon and you burn it completely, how much gas is produced? Well, our ratio has to stay the same. So we know the ratio is 3 over 11, and that has to be equal to our carbon over the gas that we produce. So 3 times 4 equals 12, so 11 times 4 is going to give us 44 grams. In other words, for every 12 grams of carbon burned, there are 44 grams of gas released. As you learned in Lesson 5, this gas is carbon dioxide, or CO2. So to put it another way, the mass of original carbon to the mass of carbon dioxide is 12 over 44. Now why is this cool? Well, check it out. Here's our periodic table of elements, which you're all at least a little bit familiar with. Take a look at carbon. Now this number down here is the atomic mass of carbon, or how many times heavier carbon is than hydrogen. So the atomic mass for carbon is 12 grams. Let's look at oxygen. The atomic mass for oxygen is 16. It's 16 times heavier than hydrogen. So now, could we figure out the atomic mass of CO2? So that's 1 carbon and 2 oxygens. C plus 2 times O. Well, C we know is 12. Oxygen is 16. So we have 12 plus 32. And what do you know? It's 44. So the ratio of 12 grams of carbon burned to 44 grams of carbon dioxide put off makes a whole lot of sense based on the mass of these elements. Don't worry if this doesn't make perfect sense yet. We're just starting to get into the really difficult, interesting stuff, and we'll be practicing it a lot. But I do hope you understand the concept that elements combine in ratios, and we measure those ratios as we weigh their masses and their volumes. In the next lesson, we're going to be making more sense of these constant chemical ratios by looking at those chemical properties and seeing if we can even predict how the ratios will turn out.